Hello everyone, welcome to recitation number 4. Now technically we already did this one on campus, but I thought I'd do an offline recording of it in case you weren't able to attend or if you just want to revise. So the main three ideas that we went through in this recitation were pumping lemma, context-free grammar or CFG for short, and pushdown automata or PDA for short. Now, technically, I skipped GNFAs. So GNFA is a way where you can convert an NFA or maybe a DFA into a regular expression. This is really important as well, but maybe we'll do it next time because for now I feel these ideas are more important to know. So you can better understand what's going on in the main lectures. Okay, so far what have we done? We've introduced DFAs, like when we were the main idea here when we learned about states where I can manipulate and make fake memory with even A, odd B, stuff like that. Then on top of that, we built the NFA. Now, what we mentioned was, okay, suppose you have some machine X in your DFA. Like imagine it's a set of DFAs, all DFA machines, and some other set Y, all NFA machines. Now, if we say, hey, let some X belong to the DFAs, so it itself is some DFA machine, then that X must also be an NFA, right? Because what is really NFA? It's technically a DFA, but without the restrictions. You know, like with DFA, if you have some transition 1, you can't have it more than once, right? And for every symbol in your alphabet, you have to have exactly one transition, and you can't have the epsilon, etc. So it's all this stuff. So if you simply don't do those restrictions, like if you stay with the rules of the DFA, it's still technically an NFA. You simply didn't use those that flexibility. However, the other way around is not true. Like if I say I have some Y that's an NFA, it doesn't have to be a DFA as well. It could be, again, if we don't use the flexibility, but if we do, like if I have an epsilon, well, it's no longer a DFA. So not necessarily that Y has to be a DFA. Okay. However, this set makes me feel like the way that we have it in front of us, it makes us feel that NFA is stronger, but not really. It is more flexible, but in terms of strength, what really makes something stronger is the language. And both these, an NFA and an NFA, they both recognize the same languages. And we actually did this last week when we said, hey, for every Y that's an NFA, there is some. So if for every Y that's an NFA, there does exist some Y prime that's a DFA such that the language that Y recognizes is the same language that Y prime recognizes. What am I saying here? The algorithm that we learned last week, if you remember, if you have some NFA, you can convert it into a DFA. Well, that simply means, okay, anything that you can do with an NFA, you can transition it into or transform it into a DFA, then hey, they both recognize the same language. So this is what we're saying here. If you have a machine that's an NFA, technically you can find some other machine that's a DFA and they both have the same language. Okay. However, there are some things that NFA and DFA can't recognize, like a ceiling. So if you remember, we talked about AN, BN, which is some number of A's followed by some number of B's, but that number is exactly the same. So it's like 5 A's, maybe followed by exactly 5 B's, etc. And could be anything. But this is a problem with NFA and DFA because we can't do that. The best we could do is something maybe like this. You read A, then an epsilon, then you read some B's, and you accept. This is technically A star, B star, and this is the best that we can do. I can't really control the number of A's and the number of B's. Another thing that I can't control is, for example, W reverse. Imagine W is any string. So if your alphabet is maybe A and B, W could be AAB, W reverse is BAA. So this is technically like the language of palindromes. That also I can't do in the DFA or NFA because it requires for me to memorize a sequence of characters, then see that sequence in reverse. So these are ceilings for NFAs and DFAs. Now we're going to see how we can prove them. So these technically are not regular expressions because for NFAs and DFAs, they recognize the regular languages, and the regular expressions also recognize regular languages. So if you have some regular expression, that means you can make an NFA or DFA for it. But if you have something like AN or BN, which is not really a regular expression, we're going to have to define something different for it. But first, let's find an official way to prove that it's not regular. And hopefully, as we keep going, you'll see we're getting wider and wider with the scope of this automata hierarchy, and we get closer to really answering that question, which is, what is a computer? Like, what is the bare minimum bones I need to define this machine? Okay, so now a way to prove that A and Bn is not regular is by using the pumping lemma. What is the pumping lemma? It's a method to prove that a language is not regular. So the steps are as follows. First, you have to assume that L is regular. Like with any proof that has to do with contradiction, we first assume that that the language is regular. Remember, the goal is to prove that it's not. Well, let's assume that it is. And hopefully later we'll be able to reach some contradiction. Now, if we assume that L is regular, the pumping lemma tells us this. There exists some pumping length B such that if you have some string S that belongs to your language and it is of at least length P, the following should be true. So what I'm saying, you have to assume you have some S that belongs to your language. This S has to have at least length P, so like some arbitrary number P. And this S can be broken down into X, Y, Z. Now, what can I get from this? Y has to be positive. So the Y, the part of the string, has to be strictly positive. Its size, so it can't be empty. XY has to be less than my string length, B. And the most important part, or really the part that, they're all important, but the part that actually leads me to the contradiction is this. For every I, x, y power I, z has to stay in your language. Okay. Now I don't know what A is. Probably meant L here. So it has to stay in your language. Okay. And I could really be anything that's positive. I could be 0 or I could be more than 1. If let's say if you chose I to be 1, you simply still have the same string. But if you chose I to be something like 2, then you're making a new string S prime, which is xy squared or xyz. And this, by the pumping lemma, it has to stay in the language, but this is where the contradiction will happen. When we make S prime, it's actually not going to be in the language. It's going to not belong due to some reason, and that's your contradiction. The pumping lemma says this new S prime has to stay in the language, but for some reason it doesn't. Easiest way to understand this rule is just to do an example. So, consider epsilon to be my alphabet is 0 and 1, and my language is 0m110m, which is basically some number of zeros, 1, 1, some number of zeros, but this number of zeros has to be the same. I have m many zeros here, and I have m many zeros here, too. Show that it's not regular by using the pumping lemma. Well, step 1, assume that it is regular. You know, like you're doing CMPS to 11, you're doing some sort of contradiction, you have to first assume that it is regular. So by the pumping lemma, there exists some pumping length P. So like basically we rewrite this sentence. Oh, there exists something like P, such that, etc. So I'll say let some S belong to my language. Now the S that you choose, it has to be some family of strings, and it can't be specific. What do I mean? A good example would be this 0p 110p. This is a family of strings. It's in terms of p. So the length of S is 2p plus 2, which is definitely greater than p. Okay. So this is how you choose your S. It has to be a family of strings, and it has to be in general. I can't say S is, well, 3 zeros and then 1 1 and then 0 0. This is wrong. This is bad because it can't be specific. It has to be general. And in terms of p. Okay, so don't put other variables like, oh, 0p 110k. Just do it all p. Okay, and of course, an important thing, the S that you choose has to be inside your language. So this belongs to my language. This also belongs to my language, but again, it's not general, it's specific. So of course, choose something that's in your language and it's general. Don't choose something that's not even in my language. Like if I say something like S is 02p 110p, this is not a good choice because this isn't even in my language. The first S you choose has to be in your language. So if string S, which is broken down into X, Y, and Z, belongs to L. Okay. Right, so this is our string. Now we have to break it down into X, Y, and Z. So we have to say, okay, S is some, it's some X, some Y, some Z, such that X is something, Y is something, and Z is something too. But what are they? Well, if we go back to these rules real quick, the second step says, okay, so step 3 is saying xy has to be less than or equal to p. Less than or equal to p. Okay, so what does that mean? If my s is zeros 110p, and here I have p many zeros, my xy, since it starts my string, it has to be all in here. It can't cross over the 1 1 or the other 0 because I'm telling you, at max its size is p. And at the beginning of my string, I have 0p, so I can't go more than that. So x has to be some number of zeros. Y has to be some different number of zeros. It doesn't have to be the same. And z is the rest. Now, you could say z is 110p, and you'd be correct, but not completely correct, because we're saying x and y is at most p. It's not equal to p. At most, it could be p. So technically, z could take some number of zeros here. Right? Z could be some number of zeros from the first region of zeros. So here we'll say something like 0k such that I plus j plus k is p. Okay. What's next? Now we'll do part 1. Now we'll actually do the pumping. Okay, so this got broken like this because xy is less than or equal to p, so it's inside my first region. Is in first 0 region. Okay, cool. Now we keep going. I'll say let s prime. So now I'm doing the pumping, the actual pumping up. I can either pump up or pump down. Let's pump up first. So let's say s prime is y, x squared, x, y squared, z. Or like in other words, x, y, y, z. So this would be 0i, 0j, and then another 0j because like now I have two y's, and then z with the rest. Okay. However, we just like I and J and K, that's P, right? So like we can add them all together. I'll get 0P plus this extra J that we pumped up. Then 1, 1, then 0. But ask yourself, is now this inside my language or is it outside? This is no longer in my language. Why? Since P plus J does not equal P. Remember, like this number of 0 has to equal this one. Well, they're not equal. Why? Because of point 2. Since y is strictly positive, so j is strictly positive too. Like the size of y has to be strictly positive. So j, which is the number of zeros that y has to be strictly positive. So this does not belong into my language. That means your original assumption was wrong. So the L is not regular. Our language is actually not regular. So real quick, just what did we do? Step 1, assume that your language is regular. This is the only assumption that we did. Since it's regular, the pumping lemma tells you that 1, 2, 3 have to be true. Like if you take some string, and if you pump it up, or if you pump it down, the output, the new string, has to stay in your language, but it did not. So this means my language is not regular. Okay? Usually I'd ask if there's any question, but there's nobody here. So during class, when we did this on campus, I guess maybe the one question would have been, are these 3 points assumptions that we're saying 1, 2, 3? Technically, they are assumptions, but the real assumption is we're assuming that the language is regular. Because of that, we get point 1, 2, and 3 are true. They're true. And point 1 is saying, oh, if you pump up or if you pump down, like if you add the y's or remove a y, it has to stay in your language, but it's not staying, so that's a problem. Right. Let's now do part 2. So we're technically what we're going to be doing now is a different way of proving that something is not regular. So there is the pumping lemma, but there is also things called closure properties. So part B is saying, using the result in part A and the closure properties for regular languages, show that this language, which is the language of palindromes, show that it's not regular. Okay, so closure properties are like intersection, concatenation. We have certain rules. So if you have some language, say LA, it's the concatenation, it's the intersection of some other language, LB, and some other language, LC. Now, the closure properties tell us this. If LA is regular, then LB and LC have to be regular too. My bad. It's actually the other way around. If the two languages are regular, okay, so it's the other way around. If the two languages LB and LC are regular, that means LA also has to be regular. So if you have two languages that are regular and you intersect them, the result also has to be regular. However, here they're telling us to prove it's not regular. So we kind of want to do the opposite or the contrapositive. So from 211, the contrapositive basically is saying, okay, I'll now negate this, or I'll negate the result, and it's going to give me the negation of the output. Or in other words, let's say, assume that if LA is not regular, so either by the contrapositive or just by logic. If I'm saying LA is not regular. What does that tell me about LB and LC? I'm saying LA is not regular. Definitely either LB or LC or both are not regular. Either one of them or both. Because if they were both regular, then LA should have been regular too. But no, I'm saying assume that LA is not regular. That must mean that one of the intersecting components have to be not regular. So that's what we want to do here. What language do I have in this case scenario? I have 0M, 110M, and I have the language of palindromes. So I only have two languages. So I'm going to have to figure out some third language myself. And I want to plug them in here into this puzzle and hopefully be able to answer the question. You can pause the video here if you'd like to think about it, or we can, before I give you the solution. Okay, so it's something like this. Now, first of all, either L, so like as a hint, either L or L1 is gonna be here. Now, if you look at it, L is sort of, it's like a palindrome itself, but it's not general. Like L1 is the general palindromes, L is like a specific type of palindrome. So L is probably gonna be here. And L1, which is language of palindromes, is gonna be here. Now, what can you intersect with the language of palindromes that'll get you this specific palindrome? Well, a way of thinking about it is try to get the general expression for this, like the general look of it, which is 0 star, 1, 1, 0 star. Think about it. If you intersect the language of palindromes with something that looks like some zeros, 1, 1, and then some different number of zeros, you're gonna get 0M, 1, 1, 0M. Now, why does this solve our problem? Well, we proved that 0M, 1, 1, 0M from part 1 is not regular. That must mean either WW reverse or 0 star, 1, 1, 0 star is not regular. However, 0 star, 1, 1, 0 star is definitely regular. First of all, it's a regular expression. That should be enough. Or we could also draw an NFA for it. So something like this. I read some zeros. I read 1. I read 1. And then I read some zeros and I accept. So a way to prove that something is regular, if a language is regular, you can simply draw an NFA for it, or a DFA for it. If you're able to do that, then you just proved that it is indeed regular. So finally, since 0 star, 1, 1, 0 star is regular, we're left with WW verse, or the language of palindromes is not regular. So that's another way of doing all of this. All right. So make sure you revise concatenation, revise union. I'm not sure about union, but I'm pretty sure that concatenation also has these closure properties. Okay, now we'll do this part so we can make sure that we understand the bumping lemma, so you can pause and try to solve these two parts yourself. So basically, we want to see if these languages are regular. Now, they're not telling you prove that they are regular. They're asking the question, are they regular or not? So maybe they are, maybe they are not. So you can pause to check if you got the idea. Okay, so part A, it is not regular. But why? Before we even dive into the bumping lemma, you could ask some sort of intuition. The reason, for example, AN, BN was not regular is because I had to store the number of A's somewhere, then read the same number of B's. So I can't store N. I don't have memory. Here, it's even worse. I and J, I have to store both of these values, the number of A's and the number of B's, because later I have to read the multiplication of these two in number of A's. So as intuition, that's maybe why it's not regular. Now, as actual practice, well, Again, step one, assume that it is regular, then say let S be some general family of strings. Now I'm going to choose this, AP, BP, and again, try to make it all P's, like no K's, no other letters, AP squared. Now you might tell me, hey, you chose I and J to be the same, isn't that wrong? No, not really. In this case, it's not wrong because all they said about I and J is that they have to be positive. They didn't say that they can't equal each other. Like you might think, oh, I'm being specific, but no. So I could have chosen AP, B2P, and then the multiplication would be 2P squared, right? This is fine, and this is also fine. Here I happen to choose I and J are the same, and here you happen to choose that J is bigger than I, because 2P has to be bigger than P. That's also fine. All they're saying is that I and J have to be greater than or equal to 0. Okay, I have my S. Now what should I do? It's the exact same thing as before. Like really using these points. What do I have? Because of point 3, X and Y are going to be all in the first A region, right? So very quickly, I can say, oh, X is going to be some number of A's. Y is going to be some different number of A's. And finally, Z, since it doesn't have to be all of it, Z is going to be the rest. It's some number of A's as well. I can write K and say that the sum of I and J and K are P, or I can say something like P minus J and minus I. That's okay as well. Like Z is the rest of them. And then BP, AP squared. And same thing as before, I'll try to pump up. This time, let's try to pump down. So I'll say S prime. So let S prime be XZ. Why XZ? Because I is greater than or equal to 0. I is greater than or equal to 0. So it could be 0. I could choose it to be 0. That would be pumping down. I could choose it to be 2, 3, 4, whatever I want. That would be pumping up. Or I can say I is 1 is not really changing anything. If you say I is 1, it stays the same as. So you're not really pumping. And by the way, this belongs to your language, and obviously the size of S is 2p plus b squared, which is bigger than b. Okay. So S prime is now going to be what? Real quickly, you can type it yourself, but actually let's just say it. X is AI and Z is the rest. So like we removed the J. Like when this I goes away with this I, really what you're left is like you removed some number of J's. Okay. Why does this not belong to my language? Well, because of point 2, Y is strictly positive, so J is positive. Again, when I say Y is positive, I mean like the size of Y, not the actual Y. Y is just some string. A string can't really be positive or negative. Okay, and P minus J, or not and, maybe so would be the better word. So since J is strictly positive, we can conclude that P minus J times P, which is P squared minus PJ, can't really equal P squared because you're removing some number from the P squared. So this is no longer in your alphabet. Why? Again, this times this no longer equals this, which is the whole point of the language. So it's no longer in my language. Then again, your assumption is wrong. So L is not regular by the pumping lemma. Okay. Now, maybe I was asked, hey, is this how it's going to be in the exam? I don't know. maybe yes, maybe no, right? Like, what's important in the recitation is we try to understand the ideas, like, oh, how the pumping lemma works, how NFAs works, how DFA works. You're gonna have to then practice yourself. Like, obviously, definitely the recitations are not enough. You're gonna have to solve the suggested problems that are on Moodle. You have to maybe try to solve some questions from the book, maybe Google some questions, etc. Okay, like maybe see it in how it will look like in MCQ format. Make sure you're always practicing. Again, the point of the recitation is to try to understand the basic concept maybe, and then you can expand on it yourself. And make sure you're always like maybe revise CMPS 211, because a lot of 257 is built on CMPS 211. If you remember, like really what a big part of CMPS 211 was all about sets, and everything we've been really doing is depending on sets. Like this language, it's basically a set under some definition, etc. Remember all the ideas about a set being countable or uncountable. Like all that stuff is also important. Okay, and like functions, like going from one set to the other, what is really all that stuff? Like if you think about it, concatenation, like maybe we did this, if some language is the concatenation of two other languages, it's really like you're saying, oh, if I take some value from here and some value from here, I'm doing like a mapping that gets me whatever L1 is, right? Things like that. Okay. Real quick, if I had chosen as double prime to be pumping up, like if I put 2y's, it would have looked something eventually like, oh, instead of removing some j, I'm like adding it instead. And obviously that would have ruined it as well. So BP, AP squared. You don't have to do multiple, like doing one pumping is enough. You don't have to do multiple. And again, maybe as triplet prime, you could have added, hey, I want to pump it more than once, so I'll add 3y's, right? This would have given you OAP plus 2j, which still ruins the whole thing. Okay, let's do part B now. Now actually part B, before like we even try to think about the pumping lemma, if you ask yourself intuition-wise, is this regular or not? You can pause. The answer is, by intuition, no, it's not. Sorry, yes, it is regular. Why? Because there's no restriction. There's no rule. Yes, there's an N and there's an M, but that's not really bad. Because all they're saying is that they're positive, right? All they're saying is that they're positive. There's no relationship. They're not saying that, oh, N is something multiplied by M or whatever, right? It's just, oh, some number of A's and then some number of B's. Unlike these are just constants, B squared and A cubed, right? So, okay, to prove this, simply I can either give a regular expression for it, that could work. Like if I say B squared A star B star A3, this represents this language. So I'm done. Maybe we have to be more specific on the rules. I'm not sure if we can say B squared. Maybe we can say something like, oh, B, AQ, A star, B star, then 3A's. This is a regular expression. Or we could say, or we could draw an NFA for it or a DFA. So I'll read a B, then I'll read another B. So now so far we've read two B's. Then I start reading the A's. I can read as many A's as I want. Then I'd read as many B's as I want. Then I have to read 3A's. Now, obviously, this is an NFA since I have a lot of transitions that are not there. But the question is, should I put a B here or should I put epsilon? So in this area, I'm reading how many A? I'm reading the A's. And in this area, I'm reading the B's. Obviously, this area is the 2B and this area is the 3A. So yeah, the important part is this, reading the A and then reading the B. So what after I'm done reading the A's and I now want to read the B's, should I put a B or should I put an epsilon? Well, if I put a B, alone, like without the epsilon, if I just say b, that would not really work. Because if you're saying b here, it's like you're forcing at least one b. But m could be 0. It's greater than or equal. So if you write a b here, it's like you're saying m is strictly positive, which is not necessarily true. So instead of b, I can say epsilon. Okay. Now you could have put epsilon comma b. That would have worked. But epsilon alone also works fine. Like, hey, I'll read my a's. When I'm done, I'll start reading my. Okay. And of course, the number of a's and b's in these two specific parts can be 0. Okay. Now, technically, when we did this on campus, this is where we stopped. But there was an extra problem that I decided I wouldn't want to do because we simply wouldn't have enough time to cover all those 3 big topics. So try to think about this, and I'll give you an idea for it. Okay, so is this regular or not? This is not regular. By intuition. Okay, so this one's intuition is going to be a bit different. We're going to have to do some examples for it. So we're going to say my language L. What is it made up of? It's a power k cubed. And k could be greater than or equal to 0. So let's try some values. If k is 0, it's basically a. So if k is 0, it's a power 0 power 3, which is just a power 0, or in other words, it's like the empty string. Like we're saying you don't have any a's. So epsilon is 1. If k is 1, you're getting a power 1 power 3, which is just a. If k is 2, we're getting a power 2 power 3, which is like a power 8. Aha. So I'm jumping from a to 8 a's. All right, if k is 3, that's a power 3 power 3, which is like, I want to say 27, right? And then maybe one last one. Maybe you'll get the idea of why, hopefully you're getting the intuition of why this might not be regular. So finally, k4, we'll get something like a power 4 power 3, which is, I think, 64. And we keep going. And as we keep going, the gaps are going to be bigger and bigger. Like we started with epsilon, then a power 8, then a power 27. Like there are really big gaps that we're skipping, right? Like you have 8 a's. So you started with epsilon, then 1a, then 8 a's, then and after a while 27 a's, and then 64 a's. Like they're really big gaps. Like what happened to the 9 a's, to the 10 a's, to the 11 a's, all the way to the 26 a's? What happened with those? So there are big gaps, and this is kind of the intuition here. We're going to choose some regular string that has some number of a's. And once we pump, we're going to pump it up in a way where it doesn't go to the next part, but goes to the gap. And we're not going to choose some specific number of a's, it has to be general. So I'll choose something like this. Say S is a power p power 3. Does this belong to my language? Yes. Why? Because my language has to be of the format a power something that's cubed. Well, this is a power something, and that something is cubed. So this does belong to my language. Okay. Next step. Obviously, its size is, I want to say p cubed, which is bigger than p. But why does this not stay in my language? Well, technically, First of all, what's the next string gonna be? Just like we did with k, like it's k, then k plus 1, then k plus 2. Those are the strings. Same thing here. The next string is gonna be, so the next one in my language is gonna be a power p plus 1 cubed. That's gonna be the next one, definitely. But what we're gonna do is once we're gonna pump up and then we're gonna fall short of that. So let's do this. Okay. Now, obviously, the x and y, they're all going to be x and y and even z, they're all going to be a's since that's all I have is a's. So x is going to be some number of a's, also y, some different number, and then z is the rest. So it's a p cubed minus I and minus j. So a is everything left. I'll pump up x, y, y, z. What happens when I do this? Well, as we've seen before, I'm gonna get an extra j, yes? So eventually, when I add everything, I and j will go with I and j. I'm gonna be left with j alone. If you're not convinced with this part, you can like do it yourself. You'll get a power p cubed plus j. Is this though less than this? Obviously, p cubed plus j is strictly bigger than p cubed, right? Because j is strictly positive. However, is p cubed plus j strictly less than p plus 1 cubed? If we can do this, then rs prime, think about it, rs prime is bigger than this string. So it has more a's than this, but it has less a's than my next string in my language. So it technically falls in the empty gap that's not in my language. If I can do that, then yes, it's not in my language. Okay. And it is y. Well, xy has to be less than or equal to p, and y has to be strictly positive. So let's think about it like this. Y is positive, the size of y, but at most, it's going to be less than or equal to p. I know xy is less than or equal to p, but we can also deduce from this that, say at max, y is less than or equal to p as well, which is the same for j. But what does this tell me? Well, back to p cubed plus j. So essentially, we're adding here p cubed too. So we're saying, p cubed is less than j plus p cubed, which is less than or equal to p plus p cubed. So basically what I did was I just added p cubed to both ends. Like this is an inequality, I added p cubed to everywhere. This is the size of s prime. This is the size of s that I began with. This is even smaller than the size of the next string. It's strictly less than the size of p plus 1 cubed. Why? I don't have the formula memorized, but if you actually expand this, it's going to have more than these. If you expand this, which is basically like p plus 1 into p plus 1 into p plus 1. I wish I have that formula memorized, but we're going to get more than this stuff. Like, okay, p times p times p, we got the p cubed. Then we have p times 1, we have p. Then the rest, 1 times p times p. I'm honestly not sure if I'm doing the expansion correctly, but just trust me, if we go ahead and Google the expansion of p plus 1 cubed, we're going to get more stuff than this. So definitely we fall short from the next string. So again, the proof was like this. First, I took S to be AP cubed. I'm telling you the next string is going to be AP plus 1 cubed. After we broke down their string, we got a string that has a size of P cubed plus J, which is bigger than this string in terms of A, but less than this. Why is it less than this? Well, J is between 0 and P. Add P cubed everywhere. So J plus P cubed is now less than this. And if we do the expansion of the next string, it's strictly bigger. This is important, but it's strictly bigger than this part. So it's not the next string, so it falls short. There go. The language is not regular. You can see maybe why I didn't solve this in class, because I wanted to, but we didn't have time. Now, it's definitely a different way of thinking. And again, is this going to come in an exam? I don't know, but at least now we know this idea of thinking, if I have big gaps, maybe I can try to pump it up or down so it falls in those white gaps. But next idea. So it's definitely going to take maybe more than our regular hour. Okay, context-free grammar. So, okay, everything we've been seeing so far, these are not regular, okay. But what are they? What can we name them? Well, a name could be context-free grammars. So context-free grammars, they're made up of variables, terminals, and rules. We'll see what they are, but we'll see actually a context-free grammar for A and Bn, which again is not regular. But it is context-free, and this is what it looks like. So what am I basically saying? All of this is a rule. The variables are usually like your capital letters. The terminals are usually your constants, which are small letters. So what's happening here? I have some variable s, and I'm replacing it with a s b. And then I can do that again. This s, I'll replace it with a s b, and this a falls down, this b falls down. Then again, I'll replace this with a s b. These fall down. And you can see, so far I've built 3 A's and 3 B's. Right. Like I have an equal number of A's and an equal number of B's. So I am getting this form A and B n. But when do I stop? Because if there has to be some stoppage, like to actually get this string, it has to be made up of all constants, all terminals. Like I can't keep a variable there. So I can come up with the rule, maybe S ends with AB. I can do that. So an extra rule that says, I'll end it with AB. But if I do that, I'm like specifying that n is now strictly positive. So I could add, otherwise I could add then the rule S ends with epsilon. So by ending with epsilon, it's like, finally this gets replaced with the empty string. So it gets replaced by nothing really. And then the 3 A's drop and the 3 B's drop. So you get 3 A's and 3 B's. Okay. So we add this rule, S ends with a terminal, epsilon. And if you have multiple rules, you can just put them next to each other like this. All right. Important idea though. Important idea here. So it's like somebody is telling you like, what exactly S? If it's easier to you, think about it like this. Imagine you have some x like mathematics. You have x is 2x plus 3, which is weird, but assume you have this. You can replace this x by itself again. So now you're replacing it by 2x plus 3 again, etc. And then you keep doing that again and again. Now, mathematically, that might not make a lot of sense, but this is really what we're doing here with the variables. I keep replacing it until finally I replace it by, I say now x is 0 or something to end it. Okay. You can pause here and try to solve these 3 problems. Okay. Right. let's see the solution. So part A. We could do some sort of reverse engineering here. So what is part A? It's like the language of palindromes, but there's like a hashtag in the middle. So this hashtag is just a simple hashtag. W is anything made up of zeros and ones. W is the reverse of that W, and then hashtag is just a hashtag. So say I'm building this string 011 hashtag 110. This is my string, and I want to reverse engineer it. A hint, you're gonna have to come up with something where, so like some rule S, and there's something here and something here. Like when you're trying to build a palindrome, I can't have a rule that's saying, oh, S goes to 1S, right? I can't have that. If I do this, well, I can just build as many ones as I want. Then there's no really symmetry. So it has to be, I have to choose something here and something here. Now this hashtag, it's probably gonna come from just the rule hashtag. So like a hint again, I'm gonna have some rule S that goes to the hashtag, like a terminal at the end to stop. Okay, well, where does this come from? It's coming from as if I have a rule 1S1, right? And this also came from the rule 1S1. So I'm left with 0S0. And this came from the rule S. I don't know if this really idea you understood the reverse engineering what I'm saying, but like I'm kind of getting that some of the rules that I have are like this. S goes to 1S1, or it goes to 0S0, or the hashtag so I can finally stop. Okay. So you can try to go it in the other route, like S goes to 1S1, or S goes to then. So you see how it's now getting pushed. If this S, I replace it by S0, 0, the ones that drop, by symmetry, they work. Like you have here 1, 0, the reverse of it is 0, 1. So it is indeed a palindrome. And if I keep going, I'll replace it now by 1S1, or maybe 0. Same thing, now 1, 1, 0, 0. If you reverse it, 0, 0, 1. So it does work. Part B. My hint for part B is divide and conquer. So it's 0, 0 star, 1, 1, 0 star. Which is really like 0 plus. It's equivalent to saying 0 plus, 1 plus. But there's a reason I wrote it like this, is so this becomes apparent. Like maybe I need to end somewhere with 0 and 1. So in class we got a lot of suggestions, but the best ones, or maybe the intuition was, or the idea here is to divide and conquer, like break it down. I first can have multiple variables. It doesn't just have to be S. I can have more than one variable. So step 1, build your zeros. So S goes to 0S. Keep building and building and building your zeros. When you're done, you want to start building your ones. So this rule is basically giving you 0, 0, 0, 0. I'm building my zeros. Now when I'm done, I want to build my ones. I can't say this though. I can't say 1S. Why? If I say this, okay, if I replace S by 0S, I'm building the zeros. Then I add the ones. Then I can use this rule again and build the zeros. You see what I'm saying? If I write it like this, I can have alternating, but it's not alternating. It's zeros, then ones. Okay. Instead, what I do is something like this. Oh, I'm done with the zeros. Then now I go to a different variable, and that variable takes care of my ones. So something like x, and then x goes to 1s. Not 1s. If I say x goes to 1s, it's like I'm back to this rule. Okay, so now x is building my ones. When I'm done, I can stop by, say, an epsilon. Now, what I currently have is building 0 star, 1 star. It's not building 0, 0 star, 1, 1 star. In order to fix that, When I go to the x, I'll actually say 0x. So like, oh, if I jump right away from s to x, at least I'll read 1, 0. Now I'm here at the x. Okay, I'll read as many x, but instead of ending with an epsilon, at least I'll end with just 1. So that way I'm reading at least 1, 1. That's it here. Part 3. Also, like here it's really maybe the divide and conquer. So what is part 3? You have some zeros, you have some ones, and then you have some zeros. But the number of 0 here and the number of 0 here, if you add them together, they have to equal the number of 1s. I'll do it like this. I'll say s goes to x and y. And x is gonna take care of the 0 and 1. So x goes to 0, x goes to 0, x 0. Sorry, 0, x1. And then it'll stop when it doesn't want anymore. And y will go to 1, y 0. Why did I do this? Okay. Imagine I started with s, I replaced it with x and y. Why did I do this? To make my life easier. Like x will take care of this part, and y will take care of this part. So x is getting replaced by, say x gets replaced 3 times. So say 0, x, 1, and then 0, 0, x, 1, 1, and then 0, 0, 0, x, 1, 1, 1, and finally it goes up to epsilon, so just 0, 0, 1, 1. However, y only gets replaced once. So y gets replaced by 1y 0, and then it just goes away. So it's now 1, 0, and then they just drop with us. The number of zeros is 3 plus 1, which is 4, which is equal to the number of ones, which is 4. So that's really the idea that's going on here. This is how we're doing it. So x and y don't have to be the same number of replacements. Like I don't have to replace 2 x's and 2 y's. I could do that, but it's not necessary. I could replace as much as I want from here and there. Hopefully that was clear. Okay. Now, what else do we want to do here? Maybe just something that could have gone wrong. Like why not do this? Why not just say s goes to 0s1 or 1s0, which is basically similar to here, right? Like the 0x1 and the 1y0, I'm just putting them together. Why not do this? Well, then you can have it alternating. So I can, okay, I have 0, 0, 1, 0s1. Then I have 0, I replace it now by this rule. So 0, 1s, 0, 1. Do you see what I'm saying? And I just now end it with epsilon. I have 0, 1, 0, 1, which is wrong. Why is it wrong? Remember, it's 0, 1, then 0. It's not alternating more than that. Okay. Now, technically, just like before, there was this part that also I didn't think we have enough time, but I'm actually not going to do it myself, so this doesn't go on for 2 hours. You can think about it yourself and let me know if you have any problems. And this is harder than the other ones. Not necessarily harder. There is a trick to it that makes it way easier. I'll just explain it. W has an even number of zeros and an even number of ones. W has an even number of zeros and an even number of ones. This is kind of similar. So I'm saying the hint now. If you want to pause it to try and solve it yourself or think yourself, you can do that now. The hint is W has an even number of zeros and an even number of ones. If we try to do what we were doing before, maybe the divide and conquer, maybe S goes to X and Y, maybe we can get somewhere, maybe not. The idea here is, remember the states, the first recitation where we're asked the question, hey, what states do I have? It's kind of the same here. W has even zeros and even ones. So it's like, the cases are I either have even A, even 0, even 1, or like they're both odd, or one is even, the other is odd, or vice versa. These are all the states I have. We'll do something similar for our variables. I'll make some variable, I'll call it S0, and if I'm at S0, it means this. If I'm at S1, I hear. S2, that means this. S3 means this. When do I stop? So for example, let's say S0 reads S0. What does that mean? I now have an odd number of zeros. So I go to here. I go to S3. Why? I read a 0. So now I have an odd number of zeros, but the ones is still even. So I go to S3. Say I'm at S2, which is even odd, and I read a 1. So I go back to S0. Why? I had even 0, but odd 1. So now I like added a new 1. So I go to S0. By the as this maybe not, so it's not confusing. Let me actually just rename it to 4, so we don't get confused with the zeros. Or maybe just S. Don't have to give it a name. So like the original. Okay. But when do I terminate? So this is the idea. This is a cool idea. You only really terminate at even. What do I mean by terminate? All the other ones are going to be made up of variables. Except for this one, I'm going to have some rule that's epsilon. Like I'll stop. Like you'll only allow it to stop when you actually have even zeros and even ones. And that's your starting variable, because when you're starting to build your string, that's all you really have. So if I read a 0, I go to S3. If I read a 1, where do you think I should go to? So I'm reading a 1. That means now I still have even zeros, but now I have an odd number of ones. So I go to here. I go to S2. You see what I'm doing? Like it's similar to the states. Like I'm drawing states and I'm jumping between them, but I'll only stop at this one. So this is like not just the hint, this is basically the solution, but you can try to flesh it out here. So that I made a hierarchy that we've been building. And an extra layer, or the next layer, is actually something called PDA, which is Pushdown Automaton. Pushdown Automaton. And technically everything we've been doing with CFGs is very relatable or related to PDAs. And actually, if you have a context-free grammar, which again, like some language is context-free, it means you have a PDA because they're equivalent. Just like before, if you had a regex or if you had a regular language, that means you had an NFA and you had a DFA. Same thing here. If you have a CFG, that means you have a PDA. So if you have A and BN, which is a CFG, that means you can represent it in a PDA or the WWR. But what is a PDA? Well, push-down automata. It's another type of machine, another made of automatas. But here we actually have some memory. So remember, with DFAs and NFAs, we didn't really have memory. We only had states, which is like a trick on like, oh, I have some fake memory. But no, here we actually have real memory, which is a stack. And with stacks, just so you remember, our operations are, I can read, I can pop, and I can push. It'll look something like this. If I want to go from one state to the other, I read A, I pop B, I push C. Read A, pop B, push C. Or say you don't want to pop anything, because if you're putting something here, you're always popping. So I can say something like this: push, read A, pop nothing, push C. Or like, hey, read nothing, pop nothing, just push some value. You can do, or maybe if you want to do it like before, where you're only reading, you can say A, I'll pop nothing, and I'll push nothing. Let's try to do A, N, and then. So this was a ceiling for NFAs and DFAs. We can't really do anything for that, but can we give a PDA for it? With PDAs, step one is always you want to push a $sign. Why? So I read nothing, I pop nothing, and I push a $sign. Well, the reason for this is you want to check if your stack is empty. So so at the very beginning, I'm putting a $1 in my stack. That's for me to know. If I ever reach the bottom and I read a $sign, that way I'll know that, my stack is empty. The reason I'm doing this is, again, all my operations are read, pop, and push. There's no fourth operation that says is empty. I don't have that option. Back to here. Okay. So push the $sign. Now I'll read my A's. So I'll read an A, I'll pop nothing, but I'll push an A into my stack. So I read an A, say I have this so far, so I have 3 A's, okay. I read an A, I push it. I read an A, I push it. I read an A, I push it. Okay. Now I go to this other place, where this time I'm going to be popping the B's. So now I read all my A's, now I'm going to be reading my B's. So I read a B, I'll pop, not a B, because what is in your stack? The symbol that's in your stack is an A. So when you read a B, you should pop an A, and you'll push nothing. Because when you're reading B's, you only want to pop the A's. So read a B. So right now I'm here, right? I read this B, I pop the A. I read a B, pop, and then the last one, pop. Finally, I'm here. What should I do now? Like, I finished parsing my string, and I'm currently here. I should check, is my stack empty? So I check, I read nothing, I'll pop the $, I'll push nothing, and then I go to the accepting state. This is almost it. But question, what should I put here when I want to transition from here to here? If you tell me, oh, I'll pop a B to transition, if you do that, then you're specifying that, it's strictly greater than, but that's not necessary. So I'll just go over there by epsilon. So I'll put it all epsilon. Oh, I'm reading nothing, I'm popping nothing, I'm pushing nothing. Again, here you're reading or pushing A. Here you're popping the A's. Why does this work though? So we can take some cases. Like this first case is the case where it's working fine. If you have 3A and you have 3B, so everything is good. As you saw, we pushed the 3A's, then we came here, we started popping the A's when we read the B's, we were done. Then we popped the $, and we went to the accepting. So it works. Okay, what about here? Say we didn't have enough, or say we had too many B's. Say I had A, and then 4 B's. Push the $, push the 3 A's, then pop 3 of the B's, and now I'm currently here. I still have 1 B to parse, and I'm currently here. Can I pop the $, and go to the accepting state? Yes, definitely I can. My stack is currently empty. I don't have anything more to pop, so I can pop the $, and I'm here in the accepting. So this gets popped. But do I accept? No. B, I still have a B to parse. I'm not done parsing. So I have to reject. This is similar to the NFA. If you're at some state and you don't have an outgoing transition, but you have something you want to read, it's like there's an imaginary transition that takes you to that trap where you simply reject. So here it doesn't work. And similar to the NFA, it takes even if it takes multiple routes, as long as it works, it works. Like here, you notice here I have a free epsilon transition that gets me from the push to the pop. Like at any moment, I can go from the push to the pop. Even if I only read 2 A's, I can, okay, go over here. But does it work? No. Because here it's for the popping, but I still have some A's to read. So that branch will reject, but as long as there's one branch that accepts, I'll accept. Okay. Type. So finally, maybe we can break this curse or the ceiling. We now are able to have some sort of machine that represents this language. And we can also represent these languages as well. Look at them for a second. Are they really different from what we just did? So this is AN, BN. This is also AN, BN, but some C's in the middle. Yes, I know there's an M, but there's no relationship between them. It's just some number of M's. So it's as if here you're sticking some extra state where you read the C's. You don't have to push them, you don't have to pop anything, you just read some C's. Here's the same thing. Oh, you push the zeros, then you pop them later, but in the middle you have to read a couple of ones. No problem. All right. I'll only solve the first one. That's actually what we, in one of the recitations, we were able only to solve one. I'll leave the rest for you to try to think about, and you can let me know if you have any problems. So actually part A and part B, we did a CFG for them. Now we're, at least for part A, we're going to do a PDA as well. Okay, you can pause if you want to think about it. The solution is something like this. Remember that, so again, it's palindromes and I have a hashtag in the middle. But remember the trick with palindromes or with stacks. Whatever you push into your stack, so say I have 110 hashtag 011. This is what I have, right? So this is W. You have your hashtag and this is W reverse. Hashtag again is just some symbol. I push a dollar at the beginning. I'll simply push W as it is. I'll read the 1, put it there. Read the 1, push it, and read the 0, push it. The cool thing about the stack, the string that you push, if you want to pop the stack and read the thing that you pushed in the beginning, it's gonna come out in reverse by itself. And like notice, W reverse. 0 here, it gets popped. 1 gets popped, and then 1 gets popped as well. So really, all I have to do is, of course, step 1, push my dollar. So say, read nothing, pop nothing, put a dollar there. And then, yeah, whatever I read for the W, I'll push it in there. So if I read a 1, I'll pop nothing and I'll push that 1. Same thing for the 0. Oh, I should have mentioned something important. So I'll read a 1, I'll pop nothing, I'll push a 1. If I read a 0, I'll pop nothing, and I'll push a 0. I'll mention the important thing after we're done with this. Okay, then when I read the hashtag, pop nothing, push nothing, I go over here and I simply start popping the W reverse. If I read a 1, pop that 1. If I read a 0, pop that 0. Finally, when there's nothing left in my stack, I'll pop the dollar and then we'll go to the accept. This is the solution. Now, even if this question was simply, if the question was, say, WW reverse without the hashtag, I simply would have put here without the hashtag epsilon, epsilon, epsilon. And I know it might be messy, but this is again with the NFA part. Like if I put an epsilon, at any point I can transition from here to here. And that's completely fine. So if I have, what I'm saying is, okay, I have 1 0 1 1 0 0 0 1 0 1 1, right? When will it know? When will the PDA know when it should stop? So I should push up to here and the rest I pop. When will the PDA know that? It doesn't. It'll simply try everything. Like first, it'll try only pushing the 1, and then it'll try popping the rest. This won't work. Like these two get popped, but I'm left with this for the parsing. Okay, then it'll try to push 2 1s and it'll pop the rest. This doesn't work because 1 can't get popped. Then it'll try this route where it pushes everything and then it pops the rest. Ah, this will work. Okay, so like the NFA, it'll try all the different routes. So PDAs are also non-deterministic. Like the D here isn't for deterministic, it's for, I think, down, push down automaton. Okay. All right, so the important thing that I wanted to mention is here I'm pushing 0 and I'm pushing 1, but I could have really pushed anything. And before I was pushing the A's here, right? I could really push whatever I want. Like you could have chosen to push an X instead. And later you would have popped an X. Or you'll push a Y and then you'll pop a Y. Or maybe if you read an A, you might have decided, oh, I want to push a B. And when I read a B, I'll pop the B. This is all just symbols, right? Like the actual A you're reading, you're not really pushing that A. You're just pushing some symbol to represent it. You're pushing something to represent like the counter of A's. But usually we'd say A just so it's easier to understand. Just like here, when we read the 0, we push the 0. When we read the 1, we push the 1. That's just so it's easier to grasp. Okay, so this is it. You can try to solve part B and part C yourself. And again, the idea here is to try to understand how PDAs work. Make sure you solve multiple problems yourself. And not just like solving problems. And make sure you revise the actual definitions. Like when we draw DFAs and NFAs, like in the recitation, just to save time, like I right away dive into maybe the drawing or the explaining. But there are official definitions, you know, like again, I don't have them memorized, but stuff like, oh, the set may be of final or the set of accepting states, right? Like any DFA that you draw or any PDA, etc., you can represent it without drawing. You can represent it simply by symbols, like saying, oh, my accepting or my final states or accepting states are like Q1 or Q2, etc. Like these are the states that at some points are accepting. And then you maybe have another symbol that's simply what are all your states. Like all my states are Q1 up to whatever, Q5. Maybe what is your starting state? Oh, my starting state is Q1, etc. And very important, what are your transitions? So there's a whole set that's called just transitions, which is basically, Q1 goes to Q2 or at the transition A, for example. Now, again, I'm drawing it, but there's a formal way of writing it. So make sure you revise those. So it's the lectures, the recitations, the suggested problems, looking up some problems yourself, the book, etc. Practice, practice, practice. Okay. See you in the next one.